Hey guys, we're going to get started on Chapter 11 now. And Chapter 11 is about categorical variables in particular. So for this, we're going to have to make use of a new distribution. We can't use a z distribution. We can't use a t distribution. We're going to be using something called the chi-square distribution. And we'll take a look at that in one moment. Let's take a look at what we have. So here's our example. We've got the company that makes milk chocolate M&Ms claims to follow the distribution that follows: 13% brown, 14% yellow, 20% orange, 16% green, 24% blue, and 13% red. Is this true? So what we would do in class is I'd give you all a package of M&Ms. You would go ahead and count them and then, maybe eat them if you want to eat them after you've counted them. Well, one year we did this. We saw we had 11 brown M&Ms, 22 yellow, 16 orange, 14 green, 12 blue, and 11 red for a total of 86 M&Ms. So we're going to write down what is a hypothesis for the significance test. It's actually pretty easy for these kinds of tests. The claimed distribution is true. Now, the claimed distribution is at 13%, 14%, 20%, etc. So alternatively, the claimed distribution is not true. Generally speaking, when we're talking about these kinds of tests, these chi-square tests, this is going to be a chi-square goodness of fit test, but the null hypothesis and the alternative hypothesis, they usually come really easily. So let's suppose that the M&M's claimed distribution is correct. If they're correct, how many of each color should we expect in our sample? Well, we're supposed to have 13% brown M&Ms. So we'll just multiply 0.13 times our 86 M&Ms, and that gives us 11.18 brown M&Ms that we were supposed to have if the distribution was true. Now we just got to do this for all of the other colors. You probably noticed as I was doing this that we were rounding everything to the 10th place. And, you do want to go just one decimal place past wherever your numbers are. So 10th place is okay here. Now our next job is to go ahead and fill out this table of values. This is going to be a lot easier with a calculator, but I'm going to go line by line and just write down what we have. So for the brown M&Ms, we observed 11. We expected 11.8. Observed minus expected is negative 0.8. Squared, that's 0.64. And then observed minus expected squared divided by expected is at 0.64 divided by 11.8, which is 0.0542. Now this one we're going to keep at 4 decimal places. Let's do the same thing for yellow. And then we'll move on to orange. And then we'll just do the rest of these. And finally, so now that we've filled out our chart, the really important row is this one at the very end. These numbers, when we add them together, they give us our test statistic. And that's 12.068. So I hope you've been paying attention through that, because that is exactly what we're going to be doing on our tests. We're going to be calculating our test statistic by, first of all, figuring out our expected values. Second of all, calculating observed minus expected. Third, squaring observed minus expected. And then fourth, dividing all of those by the expected values, then adding them all together. So, question 4 is, what value would we get for the test statistic if our sample was all very close to the expected? Well, think about it. If all of our expecteds were close to all of our observeds, then when we subtract them, we would get a very small number. And then when we squared it, we get an even smaller number. And then when we divided that by the expected again, we get an even smaller number. So, if the observed and expected were close, the test statistic would be close to 0. Conversely, what value would we get for the test statistic if our sample was very far from what was expected? Well, the test statistic would be a very large number if the observed and the expected were dissimilar. So now that we've got those basics down, we can take a look at our important ideas. Firstly, there is this idea of the hypothesis and the expected values. So remember, the hypothesis is going to be the claimed distribution is going to be true. You're going to want to write that in context, of course. So the claimed distribution for M&Ms is true would have been a better response for me. And then for alternatively, the claimed distribution for M&Ms is not true. Now, to calculate all the expected values, you're just going to multiply the probability of each category by the sample size. So always by the total number, not by the observed counts. Now, the chi-square test statistic, this is just a fancy way of writing what we already did. You're going to add together all the observed minus expected squared over the expected. Now, to calculate a p-value, you're going to need a degree of freedom because the curve that we're going to be using here, called the chi-squared curve, is multidimensional, just like our t-distribution. So we're going to have to figure out a degree of freedom. The degree of freedom is a number of categories minus 1. And then when you calculate the p-value, it's just a probability on the chi-square curve that's greater than the test statistic. Always greater than the test statistic. And on your calculator, that's chi-square CDF, test statistic to 1e99, and then a degree of freedom. So that's a lot to take in. I don't think I've said chi-square before now, but chi-square is the name of this special distribution that only works for these categorical variables. Let's check our understanding. Carrie made a 6-sided die in her ceramics class and rolled it 90 times to see if each side was equally likely to show up. So the table summarizes the outcomes of her 90 rolls. Did she make a fair die or did she make a loaded die? So part A, state the hypotheses that Carrie should test. So for the null hypothesis, we would say that the claimed dice distribution, or I suppose die distribution, where all the outcomes are equal, is true. Alternatively, we have that the claimed dice distribution is not true. So, letter B. Let's calculate the expected count for each of the possible outcomes. Well, we see that we rolled, or she rolled the die 90 times, so n is equal to 90. If this is a fair die, then all the probabilities are the same, and for a 6-sided die, that would mean that the probability is 1/6. So for each outcome 1 through 6, the expected value is 90 times 1/6. For every outcome, it's the same because we're hypothesizing that the die is a fair die. And that works out for 15, or that works out to be 15 for every of the outcomes. Let's move on to calculate the value of the chi-square test statistic. Typically, we would have all the observed and expected in this formula. adding them all together, of course. Then we're going to substitute each observed value. Then we'll substitute all the expected values. And then we'll put this long string into our calculator. And that gets us that our test statistic is 14.4. Which degree of freedom should we use? There are 6 categories. So DF equals 5. And finally, part E, use table C to find the p-value, and then what conclusion should we make? Taking out the TI-84, we're going to push second distribution, and we're going to go to the chi-square CDF, number 8. The lower is going to be our test statistic, which is 14.4. The lower is always the test statistic. Upper is going to be 1 E99. And our degree of freedom is going to be 6 categories minus 1. Yes, you can just put a 5 there if you want. Paste it, and there we go. We've got a p-value of 0.0133. Well, that p-value is definitely less than 5%. So most likely, we would be rejecting the null hypothesis and saying that we have convincing evidence for the alternative hypothesis. We'll take our standard conclusion, and then we just modify it to fit our needs. Since the p-value is less than alpha, 1.3% is less than 5%, the data supports that the claimed Dye distribution is not true. Remember that that was the alternative hypothesis. This means that the dye is not fair. And then based on the arithmetic that we did, the 2 face, that was the one that showed up 28 times. That's the one that added the most to the value of the test statistic. So there we have it, folks. Welcome to the beginning of your journey with the chi-square distribution, and I'll see you next time when we do more AP Stats. See you guys.